Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we are going to discuss another topic. So let me write today's topic. Our topic for today is microcanonical ensemble. Microcanonical ensemble. Let me encircle it. Get my pen back. We have discussed the idea of ensemble. Actually, we have been discussing in the previous lectures microcanonical ensemble, but we have not used this name. Today, we will use this name and discuss the idea in the way which it is supposed to be. Remember, when we have to give the statistical description of a system, so we have some system of interest. Let me write. I have some system now. I am interested in giving its statistical description. Now, I will always have some information available about the physical situation pertaining to this system. Then in statistical description, I will use a statistical ensemble. That means I will consider a large number of systems of identical this structure to the system of interest, right? And that representative statistical ensemble, which is constructed for the statistical description of the system of interest, must satisfy the conditions which are consistent with the information about the system in question, right? Now, since it is possible to visualize a variety of physical situations, we are led to consider a corresponding number of representative ensembles. So we can have many physical situations, so we can have many representative ensembles, right? Now, if we have an isolated system, which we have been discussing, an isolated system represents a situation of fundamental importance. It has fundamental importance. Why? And we have been discussing, as I told you, when we talked about the Boltzmann distribution of an isolated system of particles, that was an isolated system, and the ensemble which we're considering in the statistical description of that isolated system of particles, that was the microcanonical ensemble. Now, why it is of fundamental importance? Because whenever one is dealing with a situation where we have a system A which is not isolated. So if I have some system A not isolated, let me write it clearly, not isolated, but which is allowed to interact with some other system A prime. Let me use another color. So we have some other system A prime, and my A is not isolated. It is interacting with the system A prime. Now it is always possible in this situation or such situations to reduce the situation to the case of an isolated system. How? We can focus the attention on the combined system. This combined system. So even if my system A is not isolated itself, it might be interacting with some other system, A prime. I can still use the ideas pertaining to isolated system. How? I can focus attention on the combined system A and A prime, which is isolated, right? So that's why this isolated system is a situation of fundamental importance. Now, suppose the volume of the system is the only relevant external parameter. Then an isolated system of this kind consists of a number n of particles in a specified volume V. And when we are talking of isolated situation, the constant energy of the system being known to us will lie between E and E plus delta E. It is E and E plus delta E. I repeat, if I have a system which is specified by volume V, that means volume is fixed and it contains n number of particles and its energy is constant and it is lying in some range. E and E plus delta E. Remember, we are talking here in terms of quantum mechanics because we cannot precisely specify the energy of a system. It will always lie in some range. I have already discussed it in some lecture with you. Now, the probability statements about this system are then made with reference to an ensemble which consists of many such systems, all consisting of this number n of particles, all in this volume V, and all with their energy lying in the range between E and E plus delta E, right? And we know the fundamental statistical postulate asserts that in an equilibrium situation, that means when our system is in equilibrium situation, then this system is equally likely to be found in any one of its accessible states. That is the fundamental postulate. Thus, if the energy of a system in some state R, there is some state R, and the energy of the system when it is in state R, let that be ER, and let P sub R be the probability of finding the system in state R, then this PR is equal to, it is some constant C if E is less than ER is less than E plus delta E, and it is 0 otherwise. We name it equation 1. So PR is some, where C, let me write here, where C is a constant, where C is a constant. So if I have a system in state R and ER is the energy of the system in this state, then the probability PR of finding the system in state R is given by PR is C, where C is a constant. If the energy of the system ER is between E and E plus delta E, and it is 0 otherwise. That means since the system's energy system in question, its energy lies in the range E and E plus delta E, so it cannot be outside this zone. It cannot exist outside this zone. Therefore, probability of finding the system in the state in which the energy is outside this zone is 0, and the probability inside this zone is some constant C. And this constant can be determined by the normalization condition. What is that? The summation PR is 1. That means if you sum over the probabilities of finding the system in the states falling in this energy range, you will get 1 because it is not existing outside this zone, right? Now, an ensemble representing an isolated system in equilibrium. Remember, we are talking of the situation when our isolated system is in equilibrium. Now, that ensemble, which represents an isolated system in equilibrium, consists then of systems distributed in accordance with equation 1. That means in the ensemble pertaining to an isolated system in thermal equilibrium, all systems in the ensemble will satisfy equation 1. Now, it is called sometimes the microcanonical ensemble, right? I hope the situation is clear. We have already, as I told you, discussed the situation of an isolated system uh, in thermal equilibrium. And remember, sometimes we specify situation this way. We say it is NVE. Ensemble. By that we mean that, or sometimes we represent and be cautious about the notation. In the previous lectures, we used the symbol U for energy. Sometimes you can say it is the ensemble pertaining to the macro state NVU or NVE, right? That means we have some system of interest. It has a fixed number of particles. It is a fixed volume, right? Because it is isolated, and it has some fixed energy, which can be denoted by E or U. Now, to give it statistical description, first you have specified the macro state. It is in thermal equilibrium. Then, to give it statistical description, you consider an ensemble of systems which have same parameters, NVE or NVU, right? But as I told you, when we talk in terms of the quantum mechanics, we cannot specify the energy of a system precisely. We cannot say it is E. It will be in certain zone E and E plus delta E, right? Now, we will discuss another idea, and that is the idea of thermal interaction. You already know it. We have already discussed it, but since I need it in coming lectures, so I will refresh this idea. Now, if we have a macroscopic system, we have some macroscopic system. Macroscopic system means a system which has a large number of degrees of freedom. We have already discussed we can have a gas contained in some container. Even if it contains 1 mole of gas molecules, it is a macroscopic system because the number of degrees of freedom is very large. Now, if I have some macroscopic system and I want to give its description, then what we do in the description of macroscopic system, we specify some macroscopically measurable, let me write, some macroscopically measurable, independent parameters. We write it clearly here. The sum macroscopically measurable independent parameters. Let me denote them by x1 comma x2 up to xn, which are known to affect the equations of motion of this system. Now, these parameters are known as external parameters of the system. Let me repeat. I'm saying if I have some macroscopic system and we are macroscopically describing it, that means we are describing its properties disregarding the details of the molecules inside it. We're taking it in macroscopic terms. Then it is possible to specify for the system some macroscopically, which are properties of the system as a whole, and that can be measured, and they are independent of each other. Some parameters which I denoted by x1 comma x2 up to xn. These parameters are such that they affect the equations of motion of the system. That means how the system will evolve in time, that will have effect of these external parameters. That in the language of quantum mechanics means that these external parameters appear in the Hamiltonian of the system. So we call these parameters as external parameters of the system. As you know, examples of such parameters can be your system in question can be under the action of magnetic or electric field, magnetic or electric field, or both fields. So they are external parameters in that situation, right? And volume V of the system is an external parameter, right? So these external parameters, as you know, the energy levels of the system depend on the values of the external parameters. So these external parameters decide what are the energy levels of the system in question, right? So energy levels of the system depend on the values of external parameters. So when you are specifying the external parameters, you are in a way specifying the energy levels in which the system can exist. And if you are specifying them, you are specifying the energy levels. If you are changing external parameters, that will affect on the energy levels of the system, right? Now, if there is some quantum state R of the system, and it is characterized by the energy ER, we can write ER is function of the external parameters, right? Let me name it equation 1. Now, the macroscopic state or macro state of the system is defined by specifying the external parameters of the system and any other conditions to which the system is subject. As we have done it, we are just naming these things. For example, when I am saying that I have a system containing n particles which is fixed, contained in volume V and its energy is E. What I am doing, I am specifying the external parameters of the system in order to specify the energy or state, macro state. So you are specifying external parameters, and by specifying, you are specifying the macro state of the system, right? Then now the representative ensemble for the system, as I told you, is prepared in accordance with the specification of this macro state. We first specify the macro state of the system in question by specifying the external parameters. Then for the statistical description of the system in question, we construct a representative ensemble, and we know all the systems in the ensemble are characterized by the given values of the external parameters of the system in question, right? That means all systems must have same macroscopic state, right? And we know corresponding to this given macro state, the system can be in any one of a very large number of possible microstates, which are fundamentally the quantum states, right? Now let us consider two macroscopic systems, A and A prime, which can interact with each other so that they can exchange energy. Their total energy remains constant since the combiner system A superscript naught consisting of A and A prime is isolated, right? So I have system A that can interact with system A prime, but the combiner system A naught consisting of A and A prime is isolated. Now in a macroscopic description, it is useful to distinguish between two types of possible interactions between such systems, right? In one case, all the external parameters remain fixed so that the possible energy levels of the system do not change. In the other case, the external parameters are changed and some of the energy levels are thereby shifted, right? So when we consider this situation that I have a system A which can interact with system A prime, and the overall system is isolated, overall system is A naught. Now this physical situation can be of two kinds. One in which the external parameters are fixed, so the possible energy levels of the system do not change, and the other situation in which external parameters are changed and some of the energy levels are thereby shifted. Now the first kind of interaction in which the external parameters of the system remain unchanged, right? So the interaction where the external parameters of the system remain unchanged is the case of purely thermal interaction. This is the meaning of thermal interaction. So when I say system A and system A prime are in thermal interaction, by that we mean the combined system A naught has fixed external parameters, right? So the combined system A naught is isolated, and the external parameters of the whole system are fixed in thermal interaction. Now, as a result of purely thermal interaction, what will happen? Energy is transferred from one system to the other, right? And in this statistical description, we focus attention on an ensemble of similar systems A plus A prime in interaction. That is, let me use another. So I have system A and A prime. They can exchange energy with each other, but overall system, so overall whole system, which we name A naught, is isolated, right? Now we want to give the statistical description of this overall system. So what we do in the statistical description, we construct an ensemble of the systems which are identically prepared. So we will consider an ensemble, one system of A and A prime, another system in which A and A prime can interact with each other, another system A and A prime. Similarly, we can have many, and there will be some nth system in the ensemble. This is the ensemble, right? And it's understood that all systems in the ensemble are identical structure-wise to the system in question, right? Now, the energy of every system A or every system A prime does not change by precisely the same amount. That means when you consider this ensemble in the first situation, I mean in the first combined system, then you consider second combined system, third combined system, the energy of A or A prime will not change in all these combiner system by precisely the same amount. Therefore, what we do, we describe the situation in terms of the change in mean energy or average energy of the systems. Mean energy of the systems. We talk about the mean energy. I should write change in mean energy. Mean energy of the systems. Now, the mean energy transferred from one system to the other as a result of purely thermal interaction has a name that's called heat. So by heat, we mean the mean energy that transfers from one system to other system as a result of purely thermal interaction. Now, if delta E prime, not prime, bar, is the change of the mean energy of system A, change of the mean energy of system A we call that heat Q absorbed by the system. So we write Q is delta E bar as the heat absorbed by the system. This heat can be negative as well as positive. Minus Q is the heat given off by the system. Now, since the combined system A plus A prime is isolated, therefore, we can write delta E bar plus delta E prime bar is equal to 0, where delta E bar denotes the change of mean energy of A, system A, and delta E bar represents the change in mean energy of system A prime. Since the combiner system is isolated, the sum of these changes is 0. So in terms of Q, that means Q plus Q prime is 0, or Q is equal to minus Q prime. That simply means the sum of heats absorbed by the two component systems is 0. That means heat absorbed by one is the same as the heat given off by other system, right? So it merely, this equation, let me give it a name. This equation 2, this is my equation 2. Let me check the equation numbers. This is 1. Okay, it's 2. So this equation 2 merely expresses the conservation of energy statement that heat absorbed by one system must be equal to heat given off by the other system. So I stop here. Before stopping, I will summarize today's lecture, which was very easy. So first we talked about the microcanonical ensemble. So it is basically the ensemble representing an isolated system whose macro state is specified by NV and E or NV and U. But as I told you, the energy in quantum mechanics cannot be arbitrarily precise. So its energy will lie in some range between E and E plus delta E. I told you then it has a fundamental importance because if we have a system A in interaction with system A prime and the combined system is isolated, so we can talk of the combiner system in terms of the microcanonical ensemble. Then I told you how we mathematically express it, that the if ER is the energy in state R, then the probability of finding the system in the ensemble which we construct for discussing this isolated system, that probability will be constant if the energy of the state follows in this zone, otherwise it will be zero, right? Then we talked about thermal interaction. We talked about the external parameters and said when the system is in some macroscopic system is in some state R, then the energy of that state is function of these external parameters. Then we said if we have some macroscopic system and it is in interaction with some other macroscopic system A bar and the overall system is isolated, then we can have two kinds of thermal interactions between the system A and A prime. One is the thermal interaction in which the external parameters of the system are fixed. Now to study this interaction, we can consider an ensemble of the combiner systems. Then we said we talk of the change in the mean energy of system A and system B, system A prime, and heat absorbed by one is equal to heat rejected by the other system. So this is all for today. Do not forget to like, share, and subscribe my channel. You can give comment in the comment box. Thank you. Assalamu alaikum.